Hi, in this video we're going to be talking about the hidden language of numbers, and specifically we're talking about significant figures. So in science there are really two different kinds of numbers. There are exact numbers and inexact numbers, and just by looking at them you wouldn't necessarily know. You have to know the context. So for example, for exact numbers, an example of an exact number is there are exactly 12 eggs in a dozen. Or most people have exactly 10 fingers and 10 toes. Now these numbers we know from the context that they are exact numbers. We have exactly 10 fingers, for example. But there are other examples in science where numbers aren't exactly what they appear. An inexact number is any measurement that you make, because whenever you make a measurement, there's always going to be some kind of inexactness involved in your measurement. Even if you're the best measurer in the world, you have the best measuring devices in the world, there's always some level of inexactness to your measurements. So for example, if you measured the width of a piece of paper, right, you might get 220 millimeters. If you measured it again, but you're a little bit more careful about it, you looked a little bit more closely on your ruler, you might notice, okay, actually, it's 216 millimeters, if I'm being more precise. Now let's say you pulled out like a laser level and you really got really good materials and equipment that you can measure the width of the piece of paper with, you might be able to get down to a precision that tells you that paper is actually 215.6 millimeters. So each of these three measurements are inexact. Even the last one still involves some inexactness. We don't know if that's exactly true, or if we had an even better piece of equipment that we could get even more exact than that. And the point is that every measurement that we deal with in science is going to have some inexactness to it. It's not going to be exactly correct. And so we represent that exactness with significant figures. And this is a topic that's often very confusing, but it's really because it's not exactly explicit what's exact and what's inexact, what is significant and what is not significant. But significant figures, or digits, refer to the number of digits that are known to be correct in a measurement. We know that these digits are accurate. So let's start with this rule, and this is pretty simple. Whenever you're dealing with measurements, all non-zero numbers in a measurement are significant. They are known to be correct. All right, pretty simple, straightforward, but it's very easy place to start. It gets a little bit more complicated with it after this, but let's start with 62. Let's say you measured something and you got it was 62 feet long. All right, so if we counted digits here, there's two digits here that are significant. And so I'm going to write underneath this 2 significant figures. 2 sig figs. 782, there's 1, 2, 3 digits there. All of them are not zero, and so we're going to say that is 3 significant figures. All right, 62,881. 1, 2, 3, 4, 5 digits. All of them are not zero, so all of them are known to be correct. And so there are 5 significant figures in that number. So there we have it. 3 examples. Let's get a little bit more complicated though. Let's look at some digits that are not significant. And that takes us to zeros. So the number 0 is a special kind of number in science because it could be significant or it could be a placeholder. What's a placeholder 0? These are zeros that are only used in a measurement to give information about how big or how small a number is. So for example, the world has 7,674,000,000 people in it. Now, this number right here has some digits here that are not zero. These are measured, these are known to be correct. But then after that, these zeros here are not actually part of the measurement per se. They're not actually measured and known to be correct. We don't know that there are exactly this many people in the world. These numbers here are just there to show how big this number is. It's 7 billion. And we know that because these zeros are here to show us how big the number is. We don't actually count these zeros as significant, as part of the known measurement. Another example, an atom. very, very small. How small? This. I'm not even going to read that out, but it's very small. There's a decimal point here, lots and lots of zeros here until we finally get to a non-zero number. All of these zeros in front of the 1 are not actually part of a measurement. They're not showing that we have a really, really precise measurement here. Instead, they're just showing that the number itself is very small. And so these are placeholder zeros. They're just there to show how small the number is. They're not actually known to be part of some measurement that you've made. On the other hand, what are measured known zeros? These are the ones that we actually measured when we made whatever measurement we're doing. They're known to be part of the measurement. An example could be like a TV that you buy. It has a 64.00 inch display. Okay, 64.00. These zeros here, even though they're coming at the end of the number, they're significant. We know them to be part of the measurement. We're saying that the TV is not 63.99 inches, it's not 64.01 inches. We're saying it's exactly 64.00 inches. Okay, so we would count these zeros as significant. Now, on the other hand, as another example, the thickness of a spider web is 0.00030 millimeters. It's very small. Now, in this number, we actually have both placeholder zeros and a measured zero. These at the beginning are showing how small the number is. This one at the end is part of the measurement. So we do count this one at the end as part of a significant figure. We don't count the ones at the beginning because they're just there to show how small the number is. Okay, so this is kind of like the reasoning behind some zeros being significant and some being insignificant. That's the reasoning behind it. But I want to try to break it down and make it a little bit more simple so that you don't have to think about this logic every time. You can instead just think of these rules that help you kind of identify what's significant and what's not. So there are 3 or 4 rules here that we're going to talk about that help us identify what's significant and what's not. So rule number 1, zeros that are sandwiched between non-zero digits are always significant. So if you have a 0 in the middle of 2 non-zero numbers, that 0 is always significant. So these zeros here, this 0 is significant. This 0, since it's sandwiched between the non-zero numbers, is significant. These zeros, all of them, are sandwiched between non-zero numbers, so they are significant. Some other examples of this. Rule number 2. Okay, let's look at rule number 2. Zeros that come before all non-zero digits are never significant. So we have always, now we have never. The zeros that come before, the ones that come before the non-zero digits are not significant. So we do not count these zeros as significant. They're here just show us how small the number is. These zeros are not significant. They're only there to show us how small it is. These zeros here, not significant. All of them. None of them are significant. They're not measured. They're just there to show how small the number is. So that's rule number 2. So zeros that come before all non-zero digits are never significant. All right, and then finally, rule number 3. Zeros that come after all non-zero digits are only significant if there's a decimal somewhere in the measurement. That seems a little arbitrary, it seems a little like random, but it matters because the decimal place matters in scientific measurements. When you have a decimal place in there, you're often indicating that there's going to be some extra level of precision. Okay, so for example, 83,000. These zeros right here come after the 3, so they're trailing away, they're coming at the end of the number. They're only going to be significant if there's a decimal place included in the measurement. And in this case, there's no decimal place included. Now we know that there would be a decimal place here if we continued on, but the lack of a decimal place actually matters here. Because when you put the decimal place in, you're indicating to the rest of your audience in the science world that these 3 zeros are actually measured to be true. These zeros are significant. And so in this case, we only have 2 significant figures because the zeros after do not count. These 3 zeros do count because there is a decimal place. So we have 1, 2, 3, 4, 5 significant figures here. This last example, 83.000, these three zeros, because they come after, they only count if there is a decimal somewhere in the number, and there is a decimal right here. And so because there is a decimal at all, these three zeros do count. So that's going to be 1, 2, 3, 4, 5 sig figs again. So as long as there's a decimal anywhere in the number, then all the zeros that come at the end count as significant. All right, so to sum it up, these three rules here, well, let's look at some more examples to make it more clear. This number here, 4,532,100. These zeros at the end, do they count as significant? Well, is there a decimal? No, and so they do not count. So we would have 1, 2, 3, 4, 5 significant digits here. I'll write a 5 down here and circle it just to show us. 789.000. All right, these zeros are coming at the end of the number. Are they significant? Only if there's a decimal somewhere, and there is a decimal right here. So these zeros do count as significant. 7, 8, 9 are also significant, so we have 6 significant figures here. 90,000. All right, zeros are coming at the end of the number again. They're only going to be significant if there's a decimal place included, and there's not. So we only count the first digit there as significant. This must be a rounded number. It's not, only one digit is counted as significant. All right, and this last one is written in scientific notation. 2.0 times 10 to the 8. The 0 comes at the end of the number here, and so we do count it as significant. So that's going to be 1, 2. The exponent is not part of the measurement. This is just there to show how many extra zeros would actually follow this number. This is actually showing us how many placeholder zeros should come after this. But in scientific notation, all the digits, oh, you can't really read that. That's good. All the digits in scientific notation are significant. All right, so to wrap it up here, these are the three rules with zeros. Rule number 1, zeros that are sandwiched between non-zeros are always significant. So they always count. Decimal places doesn't matter. It's just if they're in between two measured numbers here, then they are always significant. Zeros that come before all non-zero digits, the ones that are coming at the beginning of the number before there's an actual non-zero number, they're never significant. And then rule number 3, zeros that come after all non-zero digits, the ones that are at the end of the number, are only significant only if there's a decimal place somewhere in the number. And so these zeros are coming at the end of the number. There's no decimal place here, so they're not significant. This 0 is coming at the end of the number, but there's also a decimal place, and so it is significant. This one has both zeros at the beginning and the end. The ones at the end count, but the ones at the beginning never count. And so the ones at the end count because there is a decimal place over here. The ones at the beginning don't count because they're at the beginning of the number. They never count according to rule number 2. All right, so what's really going to make this make sense is by doing some more practice. So I would encourage you to do some practice with this idea. Just pick some random numbers and see if they are significant or not, how many of the digits count as significant. But that's all I've got for you in this video. So remember, how you do anything is how you do everything.